Welcome everyone. Thank you for joining us once again for the lunch seminar, AstroAI lunch seminar. I'm very excited to introduce you to Ludvig today. Ludvig we had a chat in the morning, he's doing really exciting research, spoiler alert. And he's a pre-doc at CCA. He's a student at Stockholm University. He's graduating soon, or we hope so. And then going to decoding the universe in Stanford for a postdoctoral fellowship. And he's part of many collaborations in cosmology and machine learning. He'll tell us all about it today. So welcome.
Perfect. Thank you so much for the introduction. And I'm very happy to be here to present some of the recent work that I've been doing in terms of creating this cosmic digital twin of the universe. So I thought of splitting this talk into a few different sections, and towards the end I will talk about some of the latest developments we've been doing in terms of improving the fidelity of these cosmic digital twins. Well, let me start by just talking about what these cosmic digital twins are and how we actually go about to create them in the first place. So as you can imagine, in order to create a simulation that fits our universe, we need access to how everything began. So we need the initial conditions. And what I mean by that is the 3D cube. That's typically how we run our cosmological simulations at a redshift, a very high redshift of roughly 1100. So that's at the cosmic microwave background epoch. This is the relic radiation era, where basically now we're trying to infer these primordial density fluctuations that gave rise to all the structures that we observed. Now, the question that we want to answer ultimately is, what is the cosmological model or the world model that governs the evolution of all the structures in our universe? So what we can in particular do with this approach, and I will talk a bit more about this throughout this talk, is how can we actually test our cosmological model given some cosmological parameters, and is it possible to create the structure that we observe? I like this quote by Feynman that says, from the point of view of basic physics, the most interesting phenomena are, of course, in the new places, the places where the rules do not work, not the places where they do work. That is the way in which we discover new rules. So that's what we're trying to achieve here. We're trying to see if we can reproduce all the structures, and where do we fail? Where can we not? So the cosmic digital twin is then having inferred the so-called posterior distribution, if I can use this on it, of the initial conditions X, given the cosmological model, the parameters, and the data. If we then put that into a very high resolution simulation, it can look something like this. So this is an actual simulation that is constrained by 70,000 galaxies. So the structures that you see here forming as the universe evolves are there in the real universe, or at least this is one possible realization that explains the data that we have incorporated in this simulation. So all these major clusters that you see forming, these are corresponding to the most massive galaxy clusters of today. Unfortunately, and this is something that we're currently working on, is annotating what structures are actually which ones in this particular simulation to make it more visual. But now we're also producing a new generation of these cosmic digital twin simulations, which I will talk about a bit more about. But the question that arises, how do we analyze this field, and how do we produce these initial conditions? So just as an introduction, I just wanted to compare the traditional way of analyzing this large-scale structure of galaxies, and then go into how we actually go about to infer the initial conditions. So this is one of these large-scale structure simulations. This is just now a random universe. This is the so-called cosmic web. You also see here all these filaments, the high-density regions in yellow, and you see these kind of filaments that go in between these clusters. Now, what we typically do is we look at the so-called two-point statistic, or the correlation function. So we measure the excess probability of finding two clusters with a certain separation in between them. And we can do this for many different scales. We actually do this for all possible scales. And then we compute the so-called power spectrum in Fourier space. Before I show how that one actually looks like for this field, I will show you a Gaussian random field here to your left. Maybe some of you have seen this kind of comparison. But if you compute the same thing now for the Gaussian random field. So you take the same kind of rulers, you move them around in space and compute this correlation function as a function of scale. Then get this so-called power spectrum where you now have all your large scales to the left and the small scales to your right. And you get them to match exactly. Apologies. So you see that the 2-point statistic here, the power spectrum, is not a sufficient statistic to describe everything in your field, because these one have the same Gaussian information, but there is obviously some non-Gaussian information in your large-scale structure of galaxies. So how do we go about to do that more optimally? That's where the inference of initial conditions come in. So what we try to do is we fit an entire structure information model from initial conditions and cosmological parameters all the way through a n-body simulation, through a galaxy bias that incorporates the mapping from the density field to the actual galaxies that are observed. And then we incorporate all the observational effects like redshift space distortions, instrumental effects, fiber collisions, and all other kinds of observational systematic effects you can imagine to produce the actual galaxy count data that we observed in the end.
Sorry, Ludvig.
Yes.
I missed something. So what is alpha here? Is it like do you train alpha or
Yeah,
the model?
Thanks for the question. So this alpha here corresponds typically to a few parameters. Currently, we're using 6 parameters to map from the density field to the galaxies. But this is also 6 parameters per luminosity bin. So it actually is quite a bit more so-called galaxy bias parameters than that. But they are sampled jointly during inference. So what we actually do is we have this full Hamiltonian Monte-Carlo method to infer the field of initial conditions. And these galaxy bias parameters are inferred jointly with the full set of initial conditions that gave rise to this field. And as you can imagine, this is a very high-dimensional problem. The parameters of interest in our case is all the individual pixels or voxels in your field. So typically that is at least 128 cube parameters to infer jointly. So the question then arises, of course, how do we navigate this tremendous high-dimensional space of initial conditions to find the initial conditions that give rise to the structures that we observe today? So this method that I'm talking about here is called Borg, Bayesian origin reconstruction from galaxies. Typically, we talk about either field level analysis, and I typically like to classify or define this as when you have your data on a field. So you're discretizing or gridding your data on a field. If you're also inferring the entire field itself, so you have the entire modeling or inference pipeline at the field level, I would call that field level inference. So the quantity that we're inferring is a field itself. And as you might have seen here, I put up differentiable here. That means this entire pipeline from initial conditions to the data needs to be differentiable. This is a gradient-based method because we're using Hamiltonian Monte-Carlo to basically sample these initial conditions. So we get in the end a full set of plausible initial conditions that could have given rise to the data. What we then do, as I already alluded to and showed you some of these simulations, we create a digital twin by resimulating these initial conditions at even higher resolution than we used during inference. Now you might ask how and why we do that. The question, or the answer, I would say, is that the data that comes into the inference pipeline is sky position and redshift, essentially the 3D position of your galaxies, and the luminosity. So we split them into different luminosities to essentially take into account that they can be evolving in different stages and these things. In the end, what we get from running this fully high resolution simulation is that we can test other quantities that we didn't use within the inference. So we can check then density profiles. Can we actually produce the masses of these galaxy clusters? We also get velocity fields for free because we didn't use them in the inference, but we get them as a byproduct. So now I would like to just mention a few of these examples of things that we can actually use these digital twins for. But I will also say that this part of differentiable here is quite important right now, because I will come back later on in this talk to why we're now interested in trying to go beyond this. So I would like to just say that what I'm presenting here now and some of the latest results over the last couple of years only on real applications to data, what we would like to do ultimately is go beyond what we've achieved here. But I would say that this is already a quite impressive benchmark that we have managed to establish. So what we have done is creating with Borg a data product that we call Manticore. So I'll talk about Manticore-local and Manticore-deep. The Manticore-local data product is consisting of roughly 70,000 galaxies up to a redshift of 0.06. So this is really in our cosmic neighborhood of a few hundred megaparsec over H at a fairly high resolution of 2.66 megaparsec over H. So I would like to claim that what we're doing here is a very rigorous test of cosmology. We don't only need to satisfy and match population level statistics, for example, but we also do check that because that's necessary to also pass. But as an example here, this is our constrained or posterior resimulation, the digital twin, and we check for the power spectrum that I already introduced. And we see that we're matching a random lambda CDM model for the same kind of configuration setup in terms of volume and resolution with the Manticore-local suite. But we go beyond this. We're creating this full physics laboratory, and we need to simultaneously fit all the structures in there. So to give you a more visual, we're going beyond the population level statistics all the way to fitting the exact structures of our universe. So in the bottom panel here, you see in red individual galaxies in our survey. And in the top, you see the underlying density field that has been reproduced by our simulation. So you see here in yellow, that's the coma cluster. And you're also seeing that we're producing these kind of filaments, high density regions, where there are many of these galaxies. One thing that is very powerful with this method is that we're managing, even in this zone of avoidance, this is like behind or within the plane of the galaxies, we do not really see that many galaxies in this line of sight. But our Bayesian model or construction here is then sampling from the prior of lambda CDM universes through the initial conditions, possible structures that could have formed behind where we cannot really see through our galaxy. So this is one example where we fit these structures and individual galaxy clusters.
Sorry, I have another question.
Yeah, go ahead.
Sorry to interrupt. Anybody else has questions? So far?
Yeah, please go ahead and interrupt me if you have questions.
So that's a probabilistic model then?
That is a probabilistic model.
So that's just one realization.
That is one realization.
High
That is
probability, I assume.
No, that's just one.
Okay.
Yeah.
But they all look similar enough.
They look very similar, yes. Thanks. Yeah, so that's just one. And I will come back to this, I think, later to show you the actual posteriors, for example, over cluster masses. But before this, I just wanted to mention that we also get velocity reconstructions for free. And this is very powerful because we get them from the initial conditions through our simulation, self-consistently evolving with the density field. So to give you 3 examples, we can also then zoom in and look at Coma, Perseus, Virgo, and see how, and I think this is in line of sight velocities, how these clusters are moving relative to us. And it has been shown, even though I don't have it here, but there was this paper last year on the velocity Olympics comparing the velocity reconstructions that we get from our forward modeling approach through the initial conditions with other approaches to infer the velocity field. And this was shown through a Bayesian evidence test to outperform or was more likely to explain the data by having this self-consistently evolving from the initial conditions. So I think this is very promising. And it's very useful for making peculiar velocity corrections to the distance ladder and could possibly be helpful eventually, maybe if we have sufficient resolution and going even beyond what we're doing here for the Hubble tension corrections. So this is what I alluded to. What we can also check is individual cluster masses. And now this is becoming very interesting because we can compare our prediction with complementary data sets. And this is just one of these examples that I wanted to mention. So you see here to your right, in each row, we have one galaxy cluster. We're comparing with other research work by other probes. So you have dynamical measurements of these clusters. You have X-ray, Sunova-Selzowicz, and weak lensing. And one of the things that you see immediately is that even these different methods do not really agree. So there's a large discrepancy, order of magnitude from 10 to the 14, 10 to the 15 in these masses for M200. And why I bring this up is because there was also this other paper recently, a few years ago, on the number of clusters that we have above 10 to the 15 solar masses over H. So, for example, what this tells you, if we look at this bottom row, is that if you have more than 5 of these clusters that have more mass than 10 to the 15, then that would be a very unlikely that we're residing in a very unlikely region of the universe. Given certain cosmological parameters, for example, for this cosmological parameter sigma 8, either 0.81 or 0.74, these are super tiny probabilities for having observed 5 clusters. But we're seeing with our posterior distributions, maybe I should have mentioned this, sorry, these are the ones that we're actually getting back from the Borg inference, these distributions, those are the posterior distributions of present-day structures. And we see quite a few of them, I think 7 if I counted correctly, or maybe even 8, are going beyond this 10 to the 15 with their uncertainties. So this would be highly unlikely if all of them would actually be pushed out beyond this 10 to the 15. And it's very interesting to further check at these regions in the universe, these cluster regions, how much they are sensitive to various changes in cosmological parameters. That could be very useful to say, where should we look and do further observations, or where do we need to fit our structure information models to their limits at even higher resolution to see what kind of cosmological model and the parameters within those models would actually be able to explain. So here I show one example of either modifying omega m or sigma 8 and how they are sensitive to changes in your initial density field. So I hope all these various examples showed you that what we can do here with field level inference is push beyond population-based statistics. We're going beyond power spectra, even bispectrum or other kinds of cross-correlation studies, by trying to fit the best models on the market to the data at the field level. But when I say that, it's not completely correct, and I will come back to this because we are still limited within this approach to differentiable models. And I think, yeah, right, sorry. Before I move on to talk a bit more in detail about the work that I've been mostly involved in, I also wanted to talk about one of the recent progress we've done in this kind of bubble of Manticore products with Borg. Because now, since the 2M++ data set was released in 2011, there has been a lot of galaxy surveys collecting data. And now we're currently in the process of finalizing this work, Manticore-deep, where we've incorporated 1.7 million galaxies from different surveys. So the 2M++ is very tiny part here in the middle, but then we've also incorporated SDSS BOSS to go to the very large volumes of 4 gigaparsec. So now we're probing very large cosmological volumes, but we're still trying to fit this at very high resolution of 4 megaparsec over H. But now that we go to these very large volumes, one of the things that we're missing is that we don't really have good measurements from other probes of galaxy clusters further out in the universe. That becomes very difficult, so we have to rely on other kind of data sets to see if the actual reconstruction that we have performed is a reasonable reconstruction with the real universe. So one of the things that we did was to look at the so-called cosmic microwave background, and in particular the weak lensing of those photons coming from this relic very early time of the universe, because those photons will travel through the universe, the actual large-scale structure of the universe. And this intervention by the other matter field components, when the photons are traveling through the universe, creates this so-called convergence field or convergence map that traces how much these photons were deflected. And this has been measured, for example, by Planck, but it's also being measured now by new CMB experiments. What we can do is either do exactly what I explained. We try to estimate this from the real universe through this relic radiation, or we can send these photons. We can actually try to reproduce what happened by sending these photons through the large-scale structure that we have reconstructed. So we run these resimulations of the universe, and we create shells of density fields, and then we basically propagate these photons through there, and we measure how much they were deflected in our digital universe. And there are a few benefits of doing this. We do know that galaxies are a biased tracer of the underlying matter field, and by doing this in our full forward simulation loop, given the specific galaxy bias model that we used during inference, we can basically get back the underlying matter field from which we can now actually send through the photons and see how much they are deflected. So it basically removes galaxy bias and also the redshift space distortions. There are two observational effects. But maybe more importantly, at this current stage of this project, it is a powerful validation that the Manticore density field that we have produced is actually corresponding to the real universe. So what we did to do that, I already mentioned this, but we compared this with the Planck satellite convergence map. So this is something, a data product that was produced by the Planck collaboration, roughly, I think, 6-8 years ago. And this is the preliminary map that we have produced with Manticore-deep. One of the things that you see here directly, now this is over all posterior samples and showing you the mean, is that where we don't have any constraints from the data, we're actually averaging out to the prior, which is 0. While in the regions where we do have data, this is corresponding to the CMAS footprint mostly, or SDSS, we see that we get these very prominent structures. Now, it's very difficult to see one-to-one correspondence in these maps. It was easier for the galaxy clustering, but we can do a cross-correlation for these maps and see if we're actually better than a random simulation. So this is what we did in this plot, where we basically show here the cross-correlation as a function of these multipoles. So we still have large scales to your left, and then we have smaller scales to the right. The detection in the end that we see is something like 12, 13 sigma. So that is how unlikely it would be that we would be able to form all these structures in alignment with the actual data from the Planck collaboration. So we would have to run quite a few simulations to actually be able to get this out of chance. But we see then that the Manticore reconstruction, the actual digital twin of the universe, is compatible, at least to this degree, with the data. And I should also mention that for this particular example of the CMB lensing, that kernel is actually peaking around redshift 2. And if you looked at the details, we're actually only going out to redshift 0.7 in terms of the data from Manticore-deep. So we're not even probing the full kernel of where we actually expect most of the CMB lensing signal to come from. But we're still seeing, I would say, fairly high, especially at large scales. But even here in this plot here in the middle, it's the same plot as the above, but just showing this in a different format so that you can see the small scales actually being quite significantly different from random simulations. Okay. Do we have any questions on these parts? This is the state of the art that we've managed to do on real data so far. And now I would like to shift focus slightly to go on and talk about how we can go even beyond this. Like, what are the future directions? Now, having established that creating these digital twins is actually something that we can do.
I was wondering, like, when you shared about your work on local environment versus environment that are primordial, I expect, how do you define the parameters for those two different kind of
Would you mind for some people? So you shared your work on local environment versus environment that is primordial. So I was wondering, how do you define different parameters? Because I expect the environment to be absolutely different.
You mean as a function of redshift? Yeah, that's a great question. So I mean, especially if I go quickly back to this one, this part here of redshift 0 is vastly different from redshift 0.7. And the initial condition, as I mentioned, they are at redshift 1100. So they are way further back. But there are very interesting work that has been led by some of my collaborators in terms of like looking more into the initial conditions, like do we have primordial non-Gaussianities, and how do they influence different inflationary models and these kind of research questions. But here everything is fairly present day structures. Now you do see a difference here and here in terms of how long or for how long they have evolved. So there are two things I would say here. So for this particular work, we have actually split this into different sub boxes, and we run them to different redshifts. So it's effectively creating this kind of light cone effect where structures out here at the boundaries of our data set, they have not evolved as much as the present day structures closer to us. So that's one way that we take this into account. The other one, as I mentioned, is also we split all these galaxies into different luminosity bits. And we also do this per observational catalog. So that also makes that we're inferring different galaxy bias parameters for structures that are further away to take this into account to some degree.
Thank you.
Thanks. Great. So coming back to this slide that I had earlier on, I wanted to mention some of the challenges that we had. Now, having established that this is a rigorous test of cosmology at the field level, and hopefully this Manticore-deep paper will be out fairly soon. We're currently circulating this in the collaboration, so I'm very excited to have this one out soon. And demonstrating that we can do field level inference of initial conditions from galaxy count data. We have also actually been doing this on other kind of data sets, not only galaxy counts. There have been pushes into weak lensing and other kind of data sets for the Borg algorithm, but I've not really talked about them here today. But in terms of challenges with this framework, some of this comes from from being restricted to the kinds of forward models that we can use within the simulation pipeline. So differentiable model is amazing because you can do full posterior sampling with Hamiltonian Monte Carlo, for example, but it also comes with some restrictions when you don't have access to differentiable models. So two ways to go about this is either you try to emulate this with some field level emulator. These have also been very successful at doing this, or you try to go beyond this in a different way, and that's what I will talk about today. One of these things that are in particular challenging is the galaxy bias mapping. So how do we go from the density field to the galaxies that we observe? Now, currently in Borg, when we try to do this in a differentiable fashion, this effectively comes down to mapping at every voxel. What is the density in this voxel to how many galaxies do you expect to have in this voxel in redshift space? But actually, when we run these very high resolution simulations, they end up being particles that move around in this cosmological volume. And what we want to do in the end is to group them together by their position and also how they're moving, so their velocity. If we could group them together and say, this is the cluster, these are the simulated particles that belong to this cluster, that would be an even better description of a better approximation to what's happening out in the real universe. But this is a non-differentiable process of grouping particles together. So it's not really easy to incorporate this within a differentiable framework. As always, computational speed and accuracy is very important. Speed here in terms of the framework that I mentioned, you need to run this pipeline something like hundreds of thousands of times. So you need to run a simulation extremely many times to sample the full set of initial conditions that could have given rise to the data. So the pipeline that I've been talking about roughly takes 30 seconds to a minute to run in one way. And we still get all these structures with very high fidelity, I would say, even though that is very low resolution, or it's a very small computational time compared to like most high computationally demanding simulations out there on the market, hydrodynamical simulations as an example. What we would like to do is to do joint sampling of the initial conditions and all our cosmological parameters. I alluded to this by showing you this map of how sensitive different structures are to varieties in cosmological parameters, but ultimately we would like to sample them in a joint framework. And this is currently restricted by having made some approximations to the full forward model in terms of having this phenomenological galaxy bias model as an example. Because it doesn't really take into account these cosmological parameters, while so-called halo finders that group particles together, they're actually dependent on the cosmological parameters in a different degree. So we would like to ultimately use that. So this brings me now to the third part of future directions with machine learning for inferring these initial conditions. And what we would like to use is to use the high fidelity simulations on the market, off the shelf, without having to approximate them, or possibly approximate them with accelerated forward models in terms of neural networks. So accelerated simulations is one promising direction that I've been leading some work on. Learning inverse mapping is another way where you basically just try to learn from simulations. How do you go from the end product to the initial field? Other more recent ones are generative models or field level simulation based inference, where we try to get the full posterior of these initial conditions directly from learning this mapping with diffusion models or flow matching or these kind of approaches. And what I will talk about mostly today, and something that I'm quite excited about, is neural search engines. So these are learning to optimize and ultimately learning to sample, but I will talk about more what I mean by this in a moment. So as I said, we want to use the state-of-the-art simulations to fit to data. And we can use this either by using a neural network as a predictor or by using it as a search engine. As a field level emulator, I implemented this so-called VNet convolutional field level emulator into the Borg framework that I've mentioned. This has yet to be applied to data. We're currently pushing that, but it has been verified on highly resolved simulation outputs from full n-body simulations and trying to get back the initial conditions that gave rise to those structures. So we showed in this paper almost 2 years ago now that we managed to produce a speed improvement of 100 while achieving even better accuracy than the current models that are differentiable within Borg. So we're percent level accurate to these full n-body simulations, and I think that's super cool. Something that we previously were not able to do. If we would run this with full n-body simulations, it would take roughly 40 years to complete this project that we did here. We did it in a month in terms of compute time, so it's still very expensive because it's a very high dimensional problem. So to explore that space, that is very expensive. But yeah, so in this paper, we discussed these aspects, but we were still limited by this alpha here. So how do we go from the density field to the galaxies?
How do you train? Is that your model, VNet, or does it exist? And can you tell us a little bit about that?
Yeah, so I want to actually talk about, we will use a very similar network model for the second part here. So I will come back to answering that question. But yeah, so Drew Jameson, he developed a very similar VNet model. We retrained it, but it's the same kind of architectural backbone to be more compatible within the Borg framework. But it's essentially the same, it is the same kind of framework that is already out there in these papers, and we just customized it for Borg. And the second aspect is how can we leverage, because these kind of neural networks are still making some kind of approximations. I should say they are very good. So we're achieving percent level, while other kinds of quasi n-body simulations, they are achieving like 10-15% accuracy on the smallest scales, but we're achieving percent level. So I think that is very promising, and I'm very happy if anyone would like to discuss this after the talk, because I'm not going to spend too much time on this, but if you're interested, I'm very happy to talk more about this, and I will be here today and tomorrow. So if you have any time, I'm happy to talk. But the other question we ask is how can we go beyond this and use the best simulations on the market without any approximations at all? We don't need to retrain some kind of neural network model in case there comes a better n-body simulation out there. What if we want to use a hydrodynamical simulations? Now you might say I cannot use them in this framework that I will present in any case because they will take too long to run. That is correct, but we're no longer restricted to differentiability. So now we can focus on maybe just trying to develop faster simulations, but we don't necessarily maybe need this differentiable aspect. That's one of the things that I will at least talk about and show you how we did. So we call this algorithm learning the universe by learning to optimize, as we also released this as part of this learning the universe collaboration that I'm part of. And the aim is to optimize the cosmic initial conditions now from present day structures using non-differentiable simulations. And we use a neural optimizer instead of a gradient-based Hamiltonian Monte Carlo to navigate or search this high-dimensional space of initial conditions. So how this looks schematically is that you can put any physics simulator you have in this left box over here. So you have some initial conditions and you generate some output. So this can be halos, as you see in this lower triangle, or the full density field in the upper one. Now, I should say that the method I will present here is applicable to any other kind of physics, or field in general, where you have some inverse problem where you want to get back the initial conditions or input to your simulation, and you have some simulation that generates the data. So you can think of this as a more general framework than the cosmological application that I will talk about. You have typically some observational data that you want to compare to. So what we do in this work is just as a proof of concept, we just take the difference in data space between your data and the output of our simulator. That creates the so-called difference field, delta D. And now we've separated to have this neural optimization pipeline to your right, where we have this delta D as the input to this VNet model. It's very similar, so that's also why I mentioned I will come back to this. I will talk about this on the next slide. And then what the VNet now is trained to do is to predict the update step in the initial conditions. We also have some stochasticity here to just prevent it from getting stuck. But this is essentially a gradient descent, but by learning it. So we don't have access to the actual gradient of your simulator, but we can effectively learn it through this neural optimizer. And we can backpropagate it all the way to the initial conditions, update them, and then run this loop again. So this comes with some benefits compared to the other approach that I also think is a very interesting push and approach towards going to smaller scales. But what we're doing here is we're ensuring that we have no machine learning in the physics modeling. We're moving that out, and we're always keeping this prediction between a full simulation and the data as a validation of the optimizer. And then we have on this side the neural optimizer that is now used as an optimizer instead of a predictor. And I just want to stress that it incorporates or enables you to incorporate these non-differentiable models. Okay, so how do we actually train this? We have this VNet neural network model, and it's based on this hierarchical 3D UNet or VNet model, where you have the input in terms of boxes. You can have how many data fields as you wish, and you have 32 channels for these convolutional operations. And then as we go down in this hierarchy, so these are the smallest scales, and then here we have some downsampling operation to have larger scales, even larger scales, and the larger scales of the reconstruction.
Again.
Yes.
In the delta D, do you just do simply with density, the density of one minus the other point by point?
Yes.
Okay.
Yeah.
And then velocity just for density or for?
So I think I should have this here. Yes. So what we use in this work is the halo field. So it's the halo catalog. How many halos that would correspond to galaxy clusters essentially in the end. But how many halos do you have per pixel or voxel in 3D? And you just take the difference with your prediction and how many halos you have in the final view. We also tried and played around with this a bit. So having a mass weighted field to basically say that the most massive halos, they should really be there. Otherwise, you would have a very tiny halo that's count 1 and a very massive cluster that will also be count 1. You wouldn't have any information of which one is more plausible or which one you should actually focus on reproducing.
And so in this case, because there's more than one galaxy in each pixel, I guess, it seems like it's more physical than in other problems it would be, right? If you do these for things that are very high resolution, maybe taking the difference pixel by pixel would not be the right thing. I guess this is a longer conversation, but I wondered how you think this can.
No, I mean, it's definitely a question in terms of the resolution. Eventually, if you zoom in, eventually you will have the exact galaxy within just one pixel, and then you would just have either one galaxy in there or not, right? So that's at the end where we push this to the very high resolution limit. Right now, we can have many galaxies or halos in the same voxel. But yeah, this is definitely something that we're considering. But this in the end would correspond to galaxy counts and bringing them into different luminosity bins, because we have different masses that corresponds to different luminosities of these actually observed objects. But why this structure is very suitable for cosmology and the large scale structure is that you get this hierarchy of different scales. So you can learn both the large scale features and small scale features at the voxel level. I wanted to mention how we train this, because I think this is not the typical way to go about it. We use this cosine similarity loss that is only trying to constrain the direction in this high dimensional space. It doesn't care about the amplitude of your prediction as long as you get the correct direction. Now you might ask then, how do we actually make use of this? Because if the amplitude is not constrained, how do you know how far you will move in that direction? And we have a solution to this, but what we show in this high dimensional space is that doing this for a cosine similarity loss as compared to like a mean squared error loss that actually constrains both the amplitude and the direction is very difficult in high dimensional space. And the cosine similarity is focusing on getting the alignment in this very high dimensional space correctly. And so it penalizes misalignments, but not amplitude. Okay, so then I will come back to how we actually do this in terms of generating or reconstructing the initial conditions. But let me just first tell you how we actually generate the training data to train this. So in the top here now, we have the initial conditions sent through Gadget 4, a high resolution full M-body simulation. This is roughly 1,500 time steps for the particular resolution and cosmological volume. So this is 1,500 time steps that we would have to then back propagate through, but then store every single time integration step. That is possible in theory, but it blows up the memory if you want to store every single time evolution step on disk while running the simulation. So that is also why this in theory is not a differentiable simulation, or in practice, sorry. And here we have a halo finder, Amiga halo finder, a spherical halo finder that groups particles together. So that's the data in this proof of concept or proof of demonstration. What we then do is we perturb these initial conditions, ensuring the same variance and mean. And we just do this by having this cosine and sinus operation, because the XA is the original initial conditions, and then we sample a new white noise field, and we basically update, and we can sample how much we perturbed from the original field. And then we run this forward as well, and we collect the pairs both in initial conditions and the final conditions. So it has seen now both very large discrepancies in data space, but also very tiny discrepancies, thanks to sampling this angle between how much we should perturb. We did a study on how many pairs of these simulations you need. I think that's a very hot topic of when you train these neural networks in general, how many simulations do you need for convergence? We see that only a few hundreds is actually enough to get a very reasonable reconstruction, but we pushed it to the limit here, running these 6,000 simulations and collecting pairs of 5,000. And that seems to be, for this particular configuration of the architecture and resolution, what we can squeeze out of this. So now back to the iterative nature, how we actually do this in practice. So you take some initial guess of the initial conditions. We typically do this and show that this is the best by taking a zero field. So it has very low, well, it has zero amplitude, there's nothing in there. You run the simulation, you get zero halos. So in the first prediction, you're basically computing delta D as just the data minus zero, so it's just the data. And from that, you're trying to learn this inverse mapping of how much do you need to update the initial conditions to then match the data next time. So we do this, we start off with some guess, zero in this case, run the simulator, but we'll do this many times. Then computing this delta D, sending it through the neural optimizer to get an update step in the initial conditions. But now this was not constrained, so we need to constrain it by doing a line search operation in that direction. And we use this so-called approximate exact line search based on the golden ratio, meaning that it only requires the optimal set of evaluations in this line of sight, given that you have a convex function, which we check by doing a lot of different steps. So basically what that says is there's one optimal step, how far you should move in this direction to produce a loss that is minimum. So this is the loss in the data discrepancy. Now you can imagine that every single blue dot here, as we go in this direction of delta xt, every single blue dot is a simulation itself. So it's quite expensive. So we need to run this roughly 4 times, and we get to the minimum, and every single dot is a full-blown simulation. But then when we have done this, and we just update, we take this step size, gamma 1, and we then move on from xt to xt plus 1, and we go back and we run the simulation again, produce the data discrepancy, run it through the neural optimizer, and we iterate until we finally end up with a good reconstruction of the initial conditions and corresponding final fields. So this is the result that we get from doing this. So in the top, you see all the true fields. These are the initial conditions, density field, the velocity field, and then the halo catalog gridded. So how many actual halos we have in these different pixels. So we see that we have either 0 or 1, 2, or sometimes even 3 or 4. I think even we have more. I just, for visibility, I cropped it as 2.5 or something. But in the bottom field, you see all our reconstructed fields, and they look qualitatively very good. And we smoothed the initial conditions because at the individual pixel level, you don't see that much of correlation. Structures in the initial conditions of the early universe, they are collapsing to the present day structures. So same resolution in the initial conditions will then collapse below the resolution in your data. But one of the things that we get back, and I want to stress this again, and we'll come back to this on one of the final slides, is the velocity field. And that is something we get as a byproduct. We didn't use it as input, but by running these simulations from initial conditions forward, we get the evolution of density and velocity. And just highlighting some of these, we get this triangle up here reproduced. We get this kind of wall or along this void reproduced. We get more high density structures also reproduced. Of course, you can see some discrepancies, but this is always the case. We're trying to fit a this has not been done before. We're trying to fit a non-differentiable model to data by not having when we don't have access to the gradients. But as you see, this is just one estimate now. We don't get the full posterior. We get one estimate of the maximum likelihood that would explain this data. Yes.
Do you know how many simulations it would take to do simulation-based inference and to get similar performance?
No, that
2 orders of magnitude is so faster, right?
Right. No, that's a very good question and something that we're looking into now. I don't have exact numbers, but yeah, that's something we're considering now, pushing this to the next phase of doing actual posterior sampling to go beyond just one reconstruction.
Oh, okay. No, I meant if you were to find the optimal solution by just usual, whatever, nested sampling MCFC, or how long, like how good will you do and how many simulations would it take?
That is, yeah, we haven't actually checked that. But you mean using some kind of differentiable forward model and then comparing how we would do with an actual HMC or gradient-based method? Using maybe sampling, right? No. So you have to do a lot more simulation. Yeah, we haven't done that, but that's interesting. So I just wanted to end by showing some of these quantitative plots for the maps that I just showed you. So here you see, again, the power spectrum of the initial conditions and the final field. And as a reference, you have the lambda CDM linear power spectrum, just to show how much beyond linear theory we go. You have the ratio between the true and the prediction. And you have down here the cross correlation between the initial conditions and the final field. One thing that you see, and I think this is very interesting, is that the power in the initial conditions drop dramatically, much well, at much larger scales than you see in the final field. For the final field, we get small scale accurate to the percent level down to the smallest scales in our inference or reconstruction. But what this tells you and quantifies is this mode coupling between linear and nonlinear scales. And it tells you what information is there, even in the linear scales of the initial conditions, to explain the nonlinear structures of today. So what this tells you is you need to be careful and also, well, in this case, design initial conditions even at these very large scales in initial conditions, because these are collapsing to form the present day structures. So even though we have no power at the small scales in the initial conditions, we still manage to fit those corresponding scales in the final field. And as I mentioned, we get back velocities. So we do very well in both reconstructing the density field, and here we show the halo velocities between the reconstruction and truth. You see there are some differences, but on average we do produce them very nicely, and same kind of well, similar kind of distribution. And if you look at the individual particle velocities, either as the Eulerian momentum, so you're also shifting the velocity by where they are in space, by the position of that particle, or here as just gridding them as their Lagrangian position in the initial conditions. These are two different quantities of the velocity field. You see that the power spectrum of the velocity field is also percent level down to the smallest scales. The Eulerian momentum is slightly lower here, but you see that the Lagrangian velocity field looks very accurate, and we didn't even use this as input. So if we can, there are a lot of, in the real universe, different surveys that go about to try to infer velocities. So if we could go there and also use that as another additional data product to go into this reconstruction, we could possibly do much better even here, because we're currently not even using a single anchor for these velocities. Okay, so that brings me to the end. I'm very happy to be here, answer any questions that you might have, and if you want, we have so far produced these so-called high-fidelity Manticore cosmic digital twins. They are available at the cosmictwin.org webpage, and I'm hoping now in the future to continue pushing the improvement of these high-fidelity digital twins at even smaller nonlinear scales. Thank you for your attention.
All right, thank you so much. Sorry for the many interruptions. Hopefully some other people have questions. Anyone online or in person? Okay.
So I had a question about the learned optimizer. So I know that in general, there's lots of effort going into these meta training and learned optimizers like that. But one of the downsides or one of the challenges is they be very unstable. Like the predictions are, especially when you start doing out of distribution, like out of training distribution type tests and things like that. Have you tried, like, how stable is the optimizer, and does it work really well out of distribution?
Yeah, so we have tested that actually. So now what I've been talking about has been trained on, is coming back to here. Everything here has been generated by the same cosmological model, same simulation pipeline, and same cosmological parameters. We haven't checked model specification in terms of running this on a different kind of simulation. I think that's very difficult, but I think it could do to some degree. I think, no, that's not entirely correct. Actually, we trained it on this first order Lagrangian perturbation theory, the most efficient, simple simulation you can imagine. And we tested it on the nonlinear simulation, and it did reasonable. Of course, not as well as here, but it did decent. But the major test we did was changing the cosmological parameters for the same kind of setup of simulators. And even then, it shows very good performance. So in some cases, we increase omega m and sigma 8, we get actually more prominent structures, performed even better in terms of the cross correlation than on the fiducial set. So it seems that it has learned some kind of physical principles, like if there's a cluster here, you should change the initial conditions by this much. And it seems to be fairly insensitive to the actual cosmological parameters.
Well, that has something to do with the smoothness of the problem or something like that.
Yeah, exactly. Yeah. Cool. Thanks.
These are impressive results. Do you have hope to try and find out that things like Hubble tension eventually?
Yeah, so there has been quite a few papers recently, actually, by a collaborator of mine called Richard Stiskolek, and he's been looking into using these reconstructions to correct for the peculiar velocity field. So that is ongoing work. I think there were a few papers in the last half a year or so on this topic. I think the last one was a month ago or something, where they're trying to correct for these velocities of regions in our cosmic neighborhood. So that is ongoing work. It looks promising, but I think, yeah.
Right.
No, thanks.
Any other questions? Online, maybe? No? Okay. Please feel free to grab more sandwiches we have leftovers. And please, let's thank Ludvig again. Oh, and remember, he'll be here today and tomorrow. He'll be sitting at B304 if you want to chat with him. So just in this corridor